In this video, I'd like to explore the idea of continuously compounding interest. So to get started with this, let's take a look at the idea of investing a simple amount, $1, at 100% interest, and then just vary the number of times per year that the compounding takes place. So if compounding happens just once a year, then we have a simple calculation. This just becomes 2 to the first power, so it equals 2. If compounding happens twice per year, we get 1.5 to the second power, which equals 2.25. If m equals 10, we get 1.1 to the 10th power, which turns out to be roughly 2.5937. And here I have 1.01 to the 100th power, which turns out to be 2.704814. And then if we jump all the way up to m equals 10,000, we get 1.0001 to the 10,000 power. And the result of that calculation is 2.71846. So if you think about the pattern that we're seeing, the values are getting larger as m increases, but the amount of the jump is certainly kind of slowing down. And we can think of this as a limit problem. In fact, we're looking at the limit as m goes to infinity of the calculation 1 plus 1 over m raised to the m power. And mathematicians have discovered that this limit approaches a specific number. It's kind of a funny number, 2.71828, and then the next digits are 1828 again, but the pattern doesn't continue. There's like a 4 and then a 6 and so on. This number is similar in spirit to the value pi that you're familiar with from geometry. So pi is approximately 3.14, but the digits famously have no pattern and they keep going in random ways. In a similar way, this number does that. The digits keep going and going. It's a very special number. It's very important in mathematics, and so it's given its own letter. We call it e. This is the number e. And you can access it on your calculator in a similar way that calculators can access pi. This number e, among other things, gives us a basis for a formula for continuously compounding interest. So let's take a look at that formula and work through a couple of examples. So here we see the formula for continuously compounding interest. It's actually quite a bit simpler than the regular compounding interest formula, because we don't need to worry about how often the compounding takes place. So let's look at an example. Imagine there's an investment of $10,000 for 8 years, and it earns 5% interest compounded continuously. So P equals 10,000. R is 0.05, the annual interest rate expressed as a decimal, and time is 8, time expressed in years. So to calculate the future value A, we have 10,000 times E to the 0.05 times 8 power. So I mentioned earlier, your calculator can help you access the number e. Make sure you know how to do that on your specific calculator. If you type this calculation in, entering just this part of the calculation, we could simplify it to be e to the 0.4. And if you enter that into your calculator, you should see something like 1.4918246 98, something like that. And then our final answer is going to be that amount multiplied by 10,000. And so the amount after 8 years at continuously compounding interest is $14,918, and then with rounding, like 25 cents. The 6 has us round up. The second example is a little bit different, similar, but a little bit different. I encourage you to try to work through it before I discuss it in a couple seconds. So with this problem, we again have continuously compounding interest, this time at 10%, but we'd like to have $4,000 in the future. So 4,000 is the future amount, time is 15 years, and the interest rate is 0.1, 10%. So my formula gives me 4,000 equals some unknown amount times e to the 0.1 times 15. So we could simplify this a little bit. 0.1 times 15 becomes 1.5. And then to find the value of p, I can divide 4,000 by e to the 1.5. Or if you prefer, we could write this as a negative exponent, 4,000 times e to the negative 1.5. So again, make sure in your specific calculator you know how to calculate a value like this. And the result of your calculation should be $892.52.